Okay, thanks everyone for being here and for sticking around to the last talk in this session. I much appreciate it. As was just mentioned, my name is Jennifer Burt. I'm a staff scientist at NASA's Jet Propulsion Laboratory, and I'm here to talk to you today about some work I've been doing using MAROON-X on Gemini North. So most of my work is in planet detection and confirmation, and I'm focusing right now on, on following up planets discovered by NASA's TESS mission, which is a transiting exoplanet survey satellite. So TESS works by doing an all-sky survey where it's focusing on measuring the brightness of hundreds of thousands of stars, and then looking for these regular dips in the star's brightness that indicates the presence of a planet that's blocking out part of the star's light. Now, TESS is taking a slightly different approach to this than its predecessor Kepler, which stared at one small part of the sky for 4 years, gave us a very in-depth view of a more limited number of stars. Instead, TESS is looking at the entire sky, and it does this in an observing mode, where it looks at one swath of the sky at a time for about a month, 28 days, and then it skips over a little bit to one side, looks at the next column of the sky for a month, skips over to the next bit of the sky, and it's marched its way around the majority of the sky at this point. So this is a nice mosaic that shows the TESS map after the completion of its primary mission the first 2 years. And you can see that we get the vast majority of the southern hemisphere, much of the north. The hole that you can see on your left-hand side is because the moon gets in the way over there right now. It's very hard to measure part per million planet signatures when the moon's getting in front of you. And so we're just avoiding that for the moment. So the data that comes out of TESS looks something like this. This is a light curve for TOI 824b. This is a planet that I discovered a couple of years ago now. And so you can see the brightness measurement of the star is relatively constant over time after we've taken out the effects of instrument and spacecraft systematics and stellar variability. But then we get these regular little drops in the brightness that you can see in the top plot. The spacing between those drops, between those transits, tells you about the orbital period of the planet. And if you phase fold those so that they line up on top of each other and increase the signal to noise, then you can model the actual shape of the transit, and the depth there tells you something about the ratio between the size of the planet and the size of its host star. Now, if you know something about the star, you can then translate those parameters into the orbital separation of the planet and the actual planet radius. So TESS has been quite successful during its first the 2 years of its primary mission and its first extended mission. It's discovered over 5,000 planet candidates, and you can see those plotted above me. One of the exciting things that we are continuing to see with TESS and that we first saw with Kepler is that the majority of planets in our galaxy seem to fall in this regime between being the size of Earth and the size of Neptune. This is an interesting discovery for us as exoplanet scientists because we don't have any planets like that in our own solar system. So it's been an area of intense discovery and learning to try and figure out what these super Earths and sub-Neptunes, as we call them, seem to be made out of. This is an updated version of the mosaic I showed you just a moment ago. This includes the observations from TESS's first extended mission. So we're filling in parts of the ecliptic plane here. And a nice thing that we're learning as well about TESS is that just every part of the sky is full of planets. So if I overplot the positions of those, 4,000, 5,000 planets I just mentioned to you, on top of that figure, they really do just fill out the entirety of the sky. Now, unfortunately, while TESS is very efficient at finding planet candidates and showing us that they exist all over the sky, the thing it doesn't do is give us masses for those planets. So the vast majority of these objects, we have radii, we have orbital periods and separations. We do not know how massive they are. So on this figure above me, you can see that of the 5,000 planet candidates, only a few dozen or so, the ones in green check marks, have actually been confirmed and had their masses measured. And that's a problem because exoplanet masses enable a whole additional level of exoplanet science. They let us do things like model the interior compositions of the planets. They're required if we want to do accurate studies of the planet's atmospheres via transmissions and spectroscopy. And they help us to understand things like the planet's formation and evolution. So they're really a main parameter that we need to understand these planets as 3D objects rather than points on a graph. Now, those masses, again, don't come from TESS. They come from ground-based collaborations doing radial velocity follow-up of the stars. And so the idea with RV follow-up, which is what I specialize in, is that you will take the light from a star and you measure it with a high-resolution spectrograph. And particularly, you're looking for the positions of the absorption features in the outer cooler layers of the star's atmosphere, the black lines on this plot. If the star is kind of sitting in space and minding its own business, those lines don't move very much. But if there's a planet going around the star, then the gravitational tug of the planet causes the star to do a much smaller orbit on the interior of that two-body system. The motion of the star then red and blue shifts those lines periodically. you can see in this nice figure here. And then if we translate the locations of those lines and the shifts they make in wavelength space into velocity space, then what we would expect to see from a planet going around the star in a circular orbit in terms of the velocity is a sinusoid. So that nice plot that you can see on the right-hand side is what we're looking for. So this is the basic approach to radial velocity science. In chasing after the planets around TESS stars, we can look at the distribution of the effective temperatures of those stars to get a sense of the spectral types. And you can see that this is a somewhat bimodal distribution. TESS focuses either on M dwarfs or G stars, and there's kind of a dip in the middle. And for today's talk, I'm going to be focusing specifically on the M dwarf side of this distribution. That's because we're excited about M dwarfs for two real reasons, what we call the M dwarf advantage. The first is that it's easier to find planets around M dwarfs than it is to find them around G-type stars. That's both true in the transit sense, because a planet of the same size causes a larger transit dip around a smaller star. And in the radial velocity sense, because a planet of the same mass causes a larger RV variation around a lower mass star than a higher mass star. The other reason is because it's easier to reach planets in the habitable zone. So both of these detection methods rely a little bit on the idea of seeing the planet go around its star at least a few times. So you can detect a periodic signature that repeats consistently enough that you believe it's a planet and not just variability in the star mimicking the Keplerian signature. Now, for a planet like the Earth around the sun, you would need to watch that star for at least 3 or 4 years to see the planet go around 3 or 4 times. But the habitable zones of M-dwarf stars can be at periods as short as 10 days. And so by looking at smaller, cooler stars, we can reach planets in the habitable zone, see them orbit their stars 3 to 4 times in the time scale of just a month or 2. So that makes it a little more accessible to us. Now, if you look at the current landscape of RV instruments, which is what's shown above me, you can see that the majority of precise RV instruments are built to be optical spectrographs, the ones on the left-hand side here. But there are a few near-infrared spectrographs that are coming online on the right. The one that I'm going to be talking about today is MAROON-X, which is located at Gemini North. MAROON-X is not quite as blue optical as many of the traditional RV spectrographs. It starts its coverage more in the yellow part of the spectrum, but then extends all the way out to 900 nanometers. And that redward coverage, red optical coverage really, is really valuable for chasing after M-dwarf stars. You can see the comparison of the SED for a star like the sun in blue, and then an M-dwarf star in red at the top of this, and how the red stars really do amp up their flux coverage as we move further into the red and the near infrared. So MAROON-X has a spectral resolution of about 85,000, and like I said, it goes from 500 to 920 nanometers, so red optical spectrograph. The fiber fetish shell. You can see the throughput curves for the 2 different arms, the blue and red arm of the instrument on the left-hand side here. And again, it's really optimized to have excellent throughput in the red. And then a nice example from the team is shown on the right. This is a very eccentric Saturn mass planet around the star HD 3651. This has become a nice example for RV teams to test the performance of their instruments, because the planet's high eccentricity suggests that there's probably no other planets in the system. They would become dynamically unstable quite quickly. So you can measure this very large signal, but be confident that there are no smaller planets that are adding additional noise to the residuals of your fit. And what you can see here is that the MAROON-X data, after we fit out the model of the planet, shows very small air bars, which is very impressive, but even more so, very small RMS values. So the blue arm of the spectrograph has an RMS of just 0.6 meters per second. The red arm is getting down to below 0.4. MAROON-X is really an example where the team under-promised and over-delivered. So the original claim was, it'll do 1 meter or 2 per second, and that would be a really nice advancement in doing these red optical spectrographs, and they have blown us all out of the water with what the instrument's producing so far. So it's a really exciting instrument to be involved with. Okay, so the 2 stars in particular that I want to talk to you about today are TOI 1685 and 1693, catchy names, I know. These are both mid-M stars, so M3 types. And what you can see here are the TESS light curves for the 2 stars. The top one is the top panel on each plot is the simple aperture photometry. So you can see some bumps and wiggles in there, mostly due to instrument and spacecraft systematics. The bottom panels are after we collect that out and treat the data to handle those signals. And if you were glancing at these off the top of your head, you might not think there's anything particularly interesting going on for these 2 stars. But if you dig into the data a little bit and look for periodic signatures, then in both cases, you would find a very small but very noticeable transit. So each of these stars has one very short period planet orbiting around it. And each of these planets, based on the TESS data, is expected to be just under 2 Earth radii or so. I'll note that going forward, most of these results are preliminary. Maybe I'll have that coming up in a minute. So don't read into it too much yet, but we're excited about the early promise. So tiny planets going around M-dwarf stars should have RV signals that are large enough that we can detect them, we hope. But the challenge for these stars is that in addition to being M stars, where they have most of their light coming out in the red part of the spectrum that our optical spectrographs don't necessarily capture, they're also quite faint. So to do this kind of science well, you want a red sensitive spectrograph with high resolution and high precision on a large aperture telescope. And that's a lot of qualifiers to put together into one request, but thankfully MAROON-X on Gemini North does an excellent job of delivering on that. Oh, here we go. Okay. The preliminary results so far, these aren't quite ready for publication, but I wanted to give you a sneak peek of where we're heading. So for TOI 1685, this star actually already has its first planet published. So you might ask, why are we still investigating it? Short answer, we didn't know that the other teams were also observing it. So there are two papers out already, one from the Carmenis team, which is shown on the left, one from the IRD team shown on the right. Both of them do a very nice job of confirming that short period planet that you can see in the top figures. And they both also make note of a potential second signature in the data. Now, the Carmenis team thinks it's something like 9 to 10 days. The IRD team thinks more like 2 and a bit days. So it's a unsolved mystery so far about what exactly that second signal is. But the other thing that is problematic about these two results from a follow-up point of view is that they both have very nice 4 to 5 sigma detections on the mass. But for planets this small, if we want to really dive in and understand if they are pure rocky bodies or if they have heavy steam-like atmospheres, then you actually need something more like a 10 sigma measurement. So the folks who want to study this planet with JWST came to us and said, MAROON-X could probably do a good job of this. Could you help us get more data and do the analysis to amplify our mass measurement? So that's exactly what we did. Here's the full RV time series for this system. The first thing to note is that the MAROON-X data just has these very tiny error bars compared to everything else. So that was really encouraging to see. And in a very reasonable exposure time of something like 20 minutes per point. You get data from both sides of the spectrograph, the red and blue arms, so you get 2 points per epoch, which is very nice. And then if we fit that data with the 2-planet model and a Gaussian process that's being used to treat some of the stellar variability, we go from the 4 to 5 sigma mass measurement that we had with the 2 previous publications to more like a 10 sigma measurement in the semi-amplitude, which is very exciting. This is exactly what we were aiming for. I wish I could say we had already solved this problem of the second signal, but that's not quite true. When we do this fit and include it, we end up with a somewhat bimodal distribution in both the period and the transit epoch of the planet. So we're not entirely sure what's happening here yet. Needs a little more digging, but the transiting planet, at least where we know the exact period and time of conjugation, is pretty well nailed down. It's exciting. Second system, 1693, is not published yet, so no one's gotten a mass for this planet. We're the first ones to really chase it. Again, we have data from MAROON-X in cyan and magenta here, and then from IRD in orange. 2 seasons of MAROON-X data, again, that we've now folded together. And in this case, again, you can see that the transiting planet will have a very nice measurement at the kind of 4.5 sigma level, which is great. Again, it's a small planet. And because no star ever seems to have just one planet, there's always at least one more to make things tricky for you. Here we see a second signal at a 5 or so sigma detection level on a much longer period, more like 20 days. For both of these longer period planets, we've gone back to the TESS data and looked for signatures of them transiting, but we don't think they do transit. We've done some injection recovery tests, seems to rule out any significant detection of planets at these periods. So the longer periods and probably a slight shift in inclination from the inner planets is probably knocking them out of a transit probability, where we'd be able to see them. Okay, so that's the planet parameters that we have so far. Again, preliminary, we're updating these as we go. Hopefully there'll be a paper out later this year. But we see that the top 3 planets are all what we think are super Earth, so they're below about 10 Earth masses. And then the bottom one, that long period planet around TOI 1693, is probably more like a sub-Neptune planet, so it's a mixed structure in that planetary system. But yeah, they all have semi-amplitudes at the 2 to 3-ish level for the small planets, and then just under 7 for the larger one. And so this is, again, an example of small planets around M-dwarf stars have accessible radial velocity signals if you have the right wavelength coverage and telescope aperture to get at them. And so if we place those 2 planets on a mass radius diagram, as I've shown you here, you see that they join a relatively small set of planets from the 5,000 candidates we had. If you downscope to the confirmed planets with 4 sigma mass measurements or better, it's a couple dozen stars at most. 7 of those are TRAPPIST. that's kind of cheating, it's all one system. But these two join a relatively small population of planets, and they're going to help us better understand what's going on in these super Earths that are close into their stars and relatively highly irradiated, what they can tell us about planet formation and evolution in these small, cool M-dwarf systems. Okay, and with that, I see standing up. So TESS is producing a plethora of these kinds of systems. There are so many more of them than we have telescope time to go after right now. So I think MAROON-X and many other RV spectrographs are going to be very busy for the next many years chasing these kinds of planets. A lot of these systems exhibit signs once you start doing detailed RV analysis of additional non-transiting planets. That's both exciting and frustrating because it makes it harder to get the correct interpretation and best fit to the system, but it's not a bad problem to have. More planets is never a bad thing. Confirming these planets requires, like I said, the combination of red spectral coverage and large apertures. So Gemini North has been a really great asset in doing this. And both of these planets are great candidates for doing either transmission spectroscopy or emission spectroscopy with things like Hubble or James Webb in the future. So we're looking forward to chasing a more detailed characterization of both systems. And with that, I will say thank you very much and ask any questions you might have.
Very nice. Questions? Really? Come on. Good.
First, thanks for a great talk. That was very impressive. The data are extraordinary. That second star, it wasn't obvious that the IRD data was even from the same star. The Maroon data was so much better.
Yeah.
So my question though is, you said that MAROON-X over delivers on its specifications. Any thoughts as to why that is and what we can learn from that spectacular success?
Yeah, so I think the team was conservative when designing the instrument. MAROON-X was built to use a lot of off-the-shelf products, and so it is a little less bespoke than many of the other RV instruments that have come online in the last few years, and because of that, they were cautious about promising on what it could do. I think this was in part just humbleness maybe on their part, I'm not sure, but it was pitched always as being like a 1 meter per second level instrument, and it has just really gone above and beyond that, especially for these M-dwarf stars.
So just curious, do you think it's the control of systematics or is it the quality of the design and the parts? It sounds like you said it's off the shelf parts, so maybe it's just how they manage the systematics, but why don't we talk during the coffee break?
Yeah, absolutely.
I have a question, but before I ask, can I ask the poster flash talk people to start coming down so they can prep? There was an interesting slide, great slides. There was one with a whole bunch of big mirrors and acronyms. Could you explain the red ones?
Yeah, absolutely. This is a busy graph to take in all at once, so I apologize for that. There we go. Yeah, so this is kind of the current precision RV landscape as it stands. And so each facility, the apertures and the wavelength coverage are somewhat approximate, but they're pretty close. And so, yeah, we have kind of the traditional suite of optical-based spectrographs on the left-hand side, and then this up-and-coming field. Some of these are somewhat well-established now of near-infrared facilities on the right. And so is there anyone you're particularly interested in, or I can just give you a rundown?
Eye locator. What's eye locator? I don't know that.
Yeah, so eye locator, someone here was from Notre Dame earlier today. Eye locator is being built at Notre Dame right now. It's going to go on the Large Binocular Telescope. It is similarly a near-infrared spectrograph, but it's going to be fed by an AO system. And so one of the big science cases is trying to look for planets around binary stars where you can actually, because there are two telescopes, separate the starlight and have RVs from one star on one telescope and RVs from the other on a second.
And HPF is Hubble, I guess, right?
Yeah, the Habitable Zone Planet Finder, which is on HET and has been doing excellent work on both M-dwarf detections and stellar variability for a number of years now.
Final one is Pavi.
So Parvi is a debut instrument. This is great. I promise I didn't ask him to ask this question. So Parvi is the Palomar radial velocity instrument. It is similarly, it's pushing further into the near infrared than almost any other instrument at this point. It's an H&K spectrometer. It is also AO fed, and one of the things that makes it really interesting is that traditionally RV instruments scale with the size of the aperture. So Parvi's on the hill, the 200-inch telescope, which is quite large. But because it's fed by an AO beam, the Parvi instrument is like this big. And so that makes it much, much easier to do the thermal and pressure and stability control that you need for doing very precise radial velocity measurements. It's a lot easier to stabilize something that's the size of like a toaster oven than this is the size of a room.
Okay, great. Last call. Okay, let's thank Jennifer again.
So thank you all.